So today we're going to start in on our next chapter, chapter 19. Okay, we're going to talk about two functional groups that we've sort of talked about in passing before but never focused on. Aldehydes and ketones. All right, an aldehyde. They both are going to kind of start this discussion, this unit, of all these functional groups which contain carbonyl bonds. Okay, so all of these are going to have these carbon-oxygen double bonds. An aldehyde is specifically when that carbonyl bond is located at the end of a molecule. Or we can say that a little bit more fancy, we got a terminal carbonyl. Whereas a ketone also has that same carbon-oxygen double bond, but it's located in the middle of a molecule. Or an internal carbonyl. Okay? In terms of the chemistry of these two functional groups, they behave the same, all right? It drives me nuts that we distinguish between aldehydes and ketones. We do so for historical reasons. Some of the earliest chemistry revolved around important biological molecules like sugars, and it turns out that all the sugars in the world can be neatly divided into one of these two categories, and so these two categories have kind of stuck around, but for our purposes, we're just gonna lump them together in our mind, all right? They behave the same here. Whether that carbonyl bond is located in the middle of the molecule or at the end. All right, and that's because of something that we've already sort of talked about before. Let's look at these carbonyl bonds more closely. All right, we have this polar bond here, where our oxygen atom is pulling all that electron density away from that carbon atom. So my oxygen has a partial negative charge. My carbon has a partial positive charge. All right, so there's this phrase that you're going to hear me say about a bajillion times over this next few weeks, which is the electrophilic carbonyl carbon. All right. It's a good electrophile for two reasons. One, because of that polar bond, leaves it relatively electron deficient. Okay, but also, even kind of more importantly, why it's a good electrophile is it can accept electrons from a nucleophile without breaking its octet, because it's got this pi bond pair of electrons that it can kick onto that oxygen atom. All right, so not only is it relatively electron deficient, that's something that's important for all electrophiles, right? But it's really susceptible to nucleophilic attack because it has this leaving group pair of electrons. Okay. All right, and we'll sort of talk about reactions here in a bit. The other way that you see these really commonly in the lab are as solvents right, and that goes just right back to that same polar bond. All right, they are very commonly used as solvents of intermediate polarity. All right. Remember, back when you were introduced to aldehydes and ketones, or rather, back when you were introduced to this idea of polarity, everything was black and white, right? It fell into one of two buckets, polar or nonpolar. And when you got to organic chemistry, you kind of graduated to a more correct way of thinking of things as being on a spectrum. Where on the one end, we have our most nonpolar molecules. And on the other end, we have our most polar molecules. Right? Nonpolar solvents would be our alkanes. You actually have to have quite a few carbons in order to make it so they're not just gases. We got to get up to 4 or 5 carbons for them to be liquids at room temperature. All right, but these are just completely nonpolar because the only thing they have are those very weak dispersion forces. Our aldehydes and ketones, because of that carbonyl group, they sit kind of in the middle. They're a little bit closer to this polar end of the spectrum here. And that's because they have these dipole-dipole interactions. All right, even more polar on our spectrum here would be, for example, our alcohols, or even water would be the most extreme, and that's because they have those hydrogen bonding interactions. All right, so we kind of want to skew this a little bit closer to the polar end of the spectrum here, but importantly, they more or less sit in the middle. We consider them to be of intermediate polarity, right? And that's good because they interact with both polar and nonpolar molecules pretty well. One of the most common ways that you see your aldehyde, I guess specifically ketones in the lab, is acetone, right? Acetone is just widely used in the lab to clean glassware because it scrubs off all those nonpolar molecules that we can't get off with our water, but it also has this added benefit of it evaporates really, really easily. Do you guys clean your glassware with, you just run the stream of air over it, right? Boom, all of a sudden you got squeaky clean, dry glassware. Awesome, okay? Cool. So yes, aldehydes and ketones very commonly used as solvents as well. All right, we're gonna start sort of where we normally start when we introduce our new functional groups, and that is nomenclature. And although these behave very similarly from a chemical standpoint, we do have to distinguish between them in our nomenclature. So we're going to talk about aldehydes first. All right, so let's just take a simple example. And we're going to do an alcohol. Just to remind ourselves here, this one would be 1-butanol. And now let's oxidize this alcohol into an aldehyde. All right, and we're going to learn how to name this thing here. All right, so step 1, as always, find and name that parent chain. All right, our longest continuous set of carbons that contains that aldehyde functional group. So in this case here, we have these, 1, 2, 3 carbons. So we're up, not 3, 4 carbons. So we're going to use that prefix but to indicate that there are 4 carbons there. All right. And now we needed to learn a different suffix because we have a new functional group here. our aldehydes have the suffix Al. So OL is for alcohols, Al is for aldehydes. All right, and just like in my name of my alcohol, it's but to indicate 4 carbons. I have the AN in there. What is that telling me? All single bonds. And then I have the OL to tell me that it's an alcohol. We're going to do the same thing. We have but to tell me there's 4 carbons, and to tell me that there's all single bonds, and then our new ending al. So butanal is the name of this molecule. All right, we don't have anything different about our substituents. All right, but what about numbering our parent chain? What do we think we're going to number, from left to right or right to left? I want my functional group here to be on the lowest number. Okay? Now, what if I were to pick up this carbonyl bond and move it over to the other end? Now what am I going to call carbon 1? I'm just going to call the other one carbon 1. All right? And what if I take this carbonyl group and move it anywhere else in my molecule? Is it still an aldehyde? No. Okay. So for aldehydes, they're actually kind of convenient. In the way that they're defined, they have to be on a terminal carbon. We're always going to make that carbon 1. So instead of saying 1-butanal, it's just implied that it's on carbon 1. All right? So in this case, you don't include the locant for aldehydes. It's always going to be on carbon 1, on your terminal carbons. Right? So numbering, we do not need to include the locant. Of that carbonyl group. And then we would assemble our name all together, just like we normally did, whereas if we had our substituents, we would put them in alphabetical order. Cool. All right, so we'll practice this here in a second. Let's introduce the next functional group, ketones. All right, again, step 1, we're going to find our parent chain. We have a new functional group, ketones. They use a new suffix here, O-N-E. So a ketone has the ending -one. All right, we got nothing new about how we're going to find and name our substituents. But now we move on to step 3, where we number our parent chain. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What are we going to pick, red or blue? We want that functional group to be on the lowest number. All right, now for aldehydes, I did not have to include that number in my name. What do we think for ketones here? I do, right? Because this, for example, is 2-pentanone. If I move that carbonyl over, that would be 3-pentanone, and those are distinct molecules with distinct physical properties. They are not identical. All right, so unlike our aldehydes, for ketones, we do have to include, this is 2-pent for the 5 carbons, and for the all single bonds, and -one for that ketone functional group. So 2-pentanone. All right, and then when it comes, so for numberings, we're just going to say we must include the locant for ketones. And then if we had other substituents, we're going to assemble our parent chain, assemble our name just like we always do, put those substituents in alphabetical order. All right, so last time when we introduced a new functional group, thiols, all of a sudden we had this complication of what happens when we have 2 functional groups within our name. And now we've just added some new ones here, so we got to update our priority list. So we're going to make this little spectrum here from highest to lowest priority. Okay, and now we got 6 functional groups here, and for each one, we're going to need to talk about how we refer to it by its prefix and its suffix. All right, so now we have 6 here. Let's make this into 6 blocks. All right, so on the very end are our alkynes and our alkenes. These were a little bit distinct in that they did not have prefixes that they're referred to. Instead, you always have to refer to them by their suffix, and you just got to build it into the back of the name. Alkenes being either ENE or EN when paired with other functional groups, and our alkynes being YNE or just YN when paired with other functional groups. All right, and what we saw was that alcohols were higher priority than thiols. All right, alcohols we referred to by that OL suffix, and thiols by that thiol suffix. All right, but then when we had a mixture of an alcohol and a thiol, we no longer referred to the SH as a thiol. We referred to it by its prefix, mercapto. All right, but now we're going to add on to this list here. Now aldehydes are our highest priority functional group that we have covered. And ketones are right behind. All right, take a second and fill out the suffix portion of this table based on what we just discussed. All right, aldehydes have that AL suffix. Ketones have that own suffix. So now if we have a mixture of molecules that contains, for example, an aldehyde and an alcohol, we're going to have to refer to the alcohol by its prefix. So it's the prefix of that alcohol group is hydroxy. Okay? And then both aldehydes and ketones, that carbonyl group you refer to, if you have to, by its prefix. They both have the same one, oxo. All right, so now that we've introduced these two new functional groups, we're going to update our priority list. This is a ranking of our functional groups from lowest to highest priority. And for each one, we have how we refer to it as its suffix when it's the highest priority group, or its prefix when it's the lower priority group. Cool. I'm going to give you a second to finish this table here, and then I'll start putting down some examples. All right, so I'm going to put down some molecules, and you're going to name them for me. All right, cool. So we got a bunch of different examples to cover here. So everybody, I'm going to give you a few minutes to copy down these structures as well as to name these molecules. So let me make some space here for each of these. All right, let's go through these one by one here. So what do we got? Aldehyde or ketone? Aldehyde. So I'm going to find my parent chain. I'm going to use that suffix al. And because this is an aldehyde, I don't even have to worry about numbering my parent chain here. This would just be pent-anal. Okay. For this one, do we have an aldehyde or a ketone? Ketone. Let's find our parent chain. These 7 carbons. And I got these chlorines in there, but these are nothing special. We just treat these as substituents in our naming, specifically chlorosubstituents. All right, so now I'm going to number my parent chain. 1, 2, 3, 4, 5, 6, 7. Or the other way, 1, 2, 3, 4, 5, 6, 7. Which one do we want, the red or the blue? The red, because we're going to prioritize our functional group. So screw those substituents. Boom. All right. We're going to still have to indicate the position of those substituents in our name here. There's 2 chloro groups, so we're going to use the prefix di, all right? And don't forget, you need to put the location of both of those chlorines in your name. So not just 6-chloro, but 6,6-dichloro, 3-heptanone. All right, and we could put the 3 in the back half of the name if we really wanted to, but it would look a little weird. All right. This would be perfectly acceptable as well. Boom. Just like we can with our other functional groups. So aldehydes, we don't have to include the locant at all. We always just assume it's carbon 1. For ketones, we're going to build it into the name. All right. This one, I think everybody's probably very tempted to tell me that this is 2-butanone. Okay? All right, well, is there such a thing as 1-butanone? No, why not? Because that would be an aldehyde, all right? What if I move this over to carbon 3? Is there such a thing as 3-butanone? No, I'm just going to start numbering the other way. So most molecules, once you get more than 2 carbons, you lose that kind of ambiguity, right? Ethanol, we don't have to say 1-ethanol. We know where that OH group is going to be. For the ketones, because they have to be internal, actually this 4-carbon ketone right here, we can just say is butanone. There's only one butanone that exists. If we move that carbonyl anywhere else, it's either no longer a ketone or it's still butanone. All right, so for ketones, it's kind of weird. Up to 4 carbons, we don't have to specify the location of that functional group because it's implied. Only one way to draw it. All right, so now we got this mixture here of this alcohol group and what other one? Ketone or aldehyde? Ketone. And according to our little spectrum here, the ketone wins, right? The ketone is the higher priority functional group. So I'm going to refer to that by the suffix -one. My alcohol is the lower priority functional group. So I'm going to refer to it as a substituent, as a hydroxy substituent. All right? Because my ketone's the higher priority group, I'm going to number to prioritize that high priority group. All right, and again, that alcohol kind of loses all of its special powers in our naming here. Now it is just a hydroxy substituent. Okay, just like all the other substituents, I'm going to indicate its location in my name. So 4-hydroxy 2-pentanone. All right. My next example here, I got 2 of these here. What do we got? 2 aldehydes, 2 ketones, or an aldehyde and a ketone? These are both two aldehydes, okay? Let's find our parent chain here. 1, 2, 3, 4. All right, when we had two alcohol groups, those were diols. If we have two aldehyde groups, they're going to be dials. All right, so when I do my name here, bute, N, dial. But are we allowed to run two consonants together? No. So in this case here, just like we did with our diols, you're going to retain that E. Okay? Now you might be tempted to think that you have to put your locants in the name, but again, they have to be located on opposite sides of this molecule. So just by saying butane dial, I know one of them is on carbon 1, the other one's got to be on the opposite side on carbon 4. So again, you don't have to specify the location of those aldehyde groups in your name here, even when there's two of them. All right? And there can't be like 3 of them or something crazy like that, or it breaks our whole nomenclature scheme where we pick our parent chain. All right? So we're not going to have to worry about that special case.
Out of curiosity, would we be able to do butanol?
So in this case, because one of them isn't if we had a ketone and an aldehyde, like in our next example, we would refer to one as oxo. For an aldehyde, the only way that you're going to refer to it as an oxo group is if you have something higher priority in there. And we haven't seen any examples of that yet. So in this case, because they're both aldehydes and there's nothing higher priority in there, we're going to use the dial. All right, but in our next example here, now we have a mixture of an aldehyde and a ketone. Right? This one on the end here is my aldehyde, which is my higher priority functional group. So we're going to refer to it by its suffix Al. The other one is my ketone. So now this is the lower priority group. We're going to refer to it by its oxo prefix. So this one right here, no longer anything special about it. It is just an oxo substituent. All right, so then we're going to number our parent chain. Again, putting that aldehyde on carbon 1. I got to refer to my location of my oxo group here. So this is 4-oxo hexanal. All right, so aldehydes and ketones. First steps first, how do we name them? We got different suffixes here. For aldehydes, we use the suffix Al. For ketones, we use the suffix -one. All right? We also updated our priority list, and it turns out that these two functional groups are now on the high end of this priority list, right? So if we have anything lower in there, we're going to refer to it by its prefixes. So for example, if we had a thiol, we would refer to it as a mercapto group, or an alcohol, it would become a hydroxy group. All right, and again, they lose all kind of their special powers of being functional groups. You no longer prioritize them or any of that sort of jazz. You assemble your name in alphabetical order. So in this case here, my hydroxy goes out front, just like our other substituents, and then our 2-pentanone for that higher priority ketone group. All right. Now there are 2 special aldehydes, or one special aldehyde and one special ketone that we just got to know the name of. All right, and these are the 2 that were mentioned in your daily quiz. The smallest aldehyde is just a single carbon. Right? Most aldehydes have 1 hydrogen on that carbonyl carbon, but the smallest aldehyde that we can make here has 2. And this one you might be thinking is methanal, and that's what the IUPAC rules would say. but literally nobody calls it methanal. This is what's called formaldehyde. Likewise, our smallest possible ketone you'd be tempted to call it propanone, and nobody would have any idea. They'd be like, what? What are you talking about? Because we don't call this propanone, we call it acetone. All right, and just quite simply, the IUPAC was assembled like 60 years ago, something like that. And these two molecules were just already in widespread use prior to that. And so basically the IUPAC was like, all right, forget it. We're just going to incorporate these names into our rules here. That 3-carbon ketone, sure, call it acetone. That 1-carbon aldehyde, sure, call it formaldehyde. All right. Acetone, we already talked about, has a lot of sort of uses in the lab, especially as a solvent. Formaldehyde you might be familiar with if you've ever been in a biology class that does any dissections. It is a commonly used aldehyde that's used for, quite frankly, just preserving dead bodies. That's what we use it for here. All right? There's like a crap ton of both of these that are produced every year because they're just so widely in use. All right? And again, that's why these kind of special names have stuck. Okay? Cool. All right, we're going to close it off there. I don't want to jump into reactions at the end here. All right, so let's just talk. On Friday is our first day of November. Remember, November is sort of the month that we've said is where your chemistry and careers interview should be taking place if you had not already gotten the jump on it and done so before. All right, so what I'm going to do for Friday's class, we're kind of ahead of schedule here. I'm going to say we're not going to have lecture on Friday, and instead you're going to dedicate that time to your careers and chemistry project. All right, now, if it just so happens to be a consequence of that tomorrow's holiday is Halloween, and for those of you who with families, young siblings, children, all that stuff, get to spend that holiday with your family without having to worry about waking up early for chemistry the next day, then wow, what an amazing consequence. Who knew that was going to happen, all right? But regardless, we won't have lecture here on Friday, and I will see you all next week, all right? Cool.